So we're going to do motion in one dimension, and this is going to separate. First thing I'll talk about is distance versus displacement. Distance in this case is going to be the blue line. So if you walked from A to B on that blue path, the distance you walked is how long that blue line is. Does that make sense to everybody? Your displacement is how far you are from where you started. So that's the red line, distance from A to B. So displacement is how far you are from where you started. Distance is the actual distance of the path you walked. Does that make sense to everybody? Next thing here is speed versus velocity. Speed is the distance per unit of time, and velocity is speed plus direction or displacement per unit of time. So an example of a speed would be I'm going 10 meters per second. Example of velocity would be I'm going 10 meters per second north. You guys understand the difference between that? Instant speed versus average speed. Instant or instantaneous speed is how fast you're going at any given instant, and average speed is how fast you travel over the whole trip. So if you're at 10 seconds after you leave the house, instant speed is how fast you're going. The average speed would be how the distance you travel divided by how long it took to get there. Does that kind of make sense? So some questions over speed and velocity here. What is the average speed of a cheetah if it sprints 100 meters in 4 seconds? Per second, yep. So we're going to be 100 meters divided by 4 seconds equals 25 meters per second. And what if it sprints 50 meters in 2 seconds? Bah, stupid bell. So next question, you start from rest and accelerate at 80 to 80 kilometers per hour. Would it be possible to have an average speed of 80 kilometers per hour if you never travel faster than 80 kilometers per hour? No. Why not? Yeah. That the time you took to accelerate is always going to have an average of less than 80 kilometers per hour, so you'd have to go faster than 80 kilometers per hour to get back up to 80 kilometers per hour. Kind of makes sense to everybody? Next question, number 3. The speedometer of a car moving to the east reads 100 kilometers per hour. It passes another car that moves to the west at 100 kilometers per hour. Do both cars have the same speed? Yep. Oops. Do both cars have the same velocity? Why not? Different direction. Number 4. During a certain period of time, the speedometer of a car reads a constant 60 kilometers per hour. Is the car moving at constant speed? Yes. Is it moving at constant velocity? We don't know. How could it be changing if it was, how could the velocity be changing? Going around a curve. Number 5, in a drag race, is it possible for the car with the greatest speed at the end of the race to lose? Yes. How would that be possible? If it started the acceleration at the beginning was very slow and sped up, it's possible for the car with the greatest speed at the end of the race to lose. So that would be yes. Okay, does the speedometer of a car measure the instantaneous speed or the average speed? Instantaneous. This one's got a couple parts here. If a duck had an average speed of 0 meters per second over the time of 3 minutes, what can you say about its displacement? Displacement would be 0. What about its average speed? Unknown. if its displacement is 0, it went around in a circle and came back to the same spot, its displacement, its average velocity would be 0, but its average speed would be something non-zero. Does that make sense to everybody? So if the duck, I'm going to draw an awesome duck. So if the duck walked around in a circle during this time and came back to where it started, its displacement would be 0 because it's no distance from where it started to where it ended. But its average speed would not be 0 because it had some distance it traveled in that amount of time to go around the circle. Does that make sense? Is that a good duck? You're riding your bike on a 10-mile long path. You travel the first 5 miles at a speed of 5 miles per hour. How fast do you have to travel over the next 5 miles for your average velocity to be 10 miles per hour? There's a trick one. Okay. The answer is actually it's impossible, or you'd have to travel infinitely fast. Let me explain why here in a second. Whoops. Okay. So if we've got part 1 is 5 miles, and part 2 is 5 miles. How long did it take you to do part 1 if you went 5 miles at 5 miles per hour? 1 hour, right? So if you wanted your average speed to be 10 miles per hour, how fast would you have to complete the total of 10 miles? You have to do 10 miles in 1 hour, right? But you already used up your hour. So you'd have to do this part in 0 time.
What if the bike path is a figure 8?
So then it's infinitely fast and it magically works, right? Does this make sense to everybody? Actually, let me take... There we go. Alright, so next part is acceleration. Acceleration measures the rate at which velocity changes. So it's change in velocity over change in time. Because acceleration involves a change in velocity, there's going to be acceleration when there's a change in direction or a change in speed. Does that kind of make sense to everybody? For right now, until we get to, I think, chapter 6, or unit 6, we're just going to be dealing with a change in speed for our acceleration, and not a change in direction. You have to know that, so know that like if you change direction, there's an acceleration, but for our actual problems, we're just going to be dealing with a change in speed. Right? A particular car can go from rest to 90 meters per second in 10 seconds. What is its acceleration? 9 meters per second. So it went from, so it's going to be, when you do acceleration, it's going to be the final velocity minus the initial velocity over time. So final is 90 meters per second minus 0 meters per second, since it starts from rest, over 10 seconds. So we get 9 meters per second. And what would the unit for that be? Squared. So meters per second squared, or meters per second per second. But this is how you're almost always going to see it, meters per second squared. Alright, next one. In 2.5 seconds, a car increases its speed from 60 kilometers per hour to 65 kilometers per hour, while a bicycle goes from rest to 5 kilometers per hour. Which undergoes the greater acceleration? Same. So for the car, the change in speed or velocity is going to be 5 kilometers per hour, and for the bike, it's also going to be 5 kilometers per hour, and it's the same amount of time. So the same change in speed over the same change in time will give you the same acceleration. Question number 3. What is the acceleration of a car that drives past you at a constant velocity of 400 kilometers per hour? 0 kilometers per hour squared, I guess. That is a fast car. I didn't record that, sorry. Which has a greater acceleration, an airplane that goes from 1,000 kilometers per hour to 1,005 kilometers per hour in 10 seconds, or a skateboard that goes from rest to 5 kilometers per hour in 1 second, and the skateboard. Why the skateboard? Same change in velocity in less time. That either. So, yes, we'll have that conversation again. All right. Can an object have a westward acceleration while traveling east? The answer we decided was yes, and that means it is slowing down. And we usually say whatever direction we're traveling is the positive direction, so we'd make our acceleration if we're slowing down negative. Or we can also call it deceleration if we're slowing down, that would be negative. Or as Garrett said a second ago, it's the acceleration if you're slowing down is positive in the opposite direction, which is the same thing as being negative. So maybe for everybody else, just think of it as negative. Can an object be increasing its speed as its acceleration decreases? Yes. So an example of that would be, let's say it's moving at 10 meters per second, has an acceleration of 5 meters per second squared. After 1 second, it's going to be going 15 meters per second, but the acceleration could have dropped to 2 meters per second squared. And after another second, it'd be going 17 meters per second. The acceleration could have dropped to 1 meter per second squared. So the velocity keeps going up, the acceleration keeps going down. Does that make sense to everybody? Free fall. Free fall is a specific kind of accelerated motion in which things are moving vertically. Some important facts that are true in free fall. Acceleration is always negative 9.8 meters per second squared. On Earth. Yes, on Earth. And it does actually change depending on your elevation on Earth, but it always rounds to 9.8, so we're just going to use 9.8 meters per second squared. And down is negative and up is positive, and we ignore any area resistance right now. Later on we'll be dealing with area resistance, but not yet. This is an awesome diagram I pulled off the internet. So drop a ball, at time 0 seconds, its velocity is 0 meters per second. So after 1 second, it's 9.8. After 2 seconds, it's 19.6. After 3 seconds, it's 29.4. And you notice that the distance it travels each time keeps getting larger. Does that make sense to everybody? So some important notes about doing problems. I'm going to make that red. The velocity at the highest point is always 0 meters per second. So you throw something up. At the top, the velocity is 0 meters per second. So it stops for an instant at the very top of its flight. Does that kind of make sense to everybody? What would the acceleration be at the top of its flight? Negative 9.8 meters per second squared. What would happen if the acceleration and the velocity were 0 at the top of its flight? It would just stop there, which would be kind of cool, but unfortunately that's not what actually happens. So if the velocity was and acceleration was 0 at the top of the flight, it would just stop at the top of its flight because the velocity wouldn't be changing because there'd be no acceleration. All right, this next one is important and drives me kind of crazy, and kids always do it. When we talk about the final velocity of an object hitting the ground, we mean the instant before it hits the ground, not like after it's hit the ground and stopped. So if we were to, for example, throw Jake off a cliff, that's Jake. Ah! No spikes. And an alligator.
I like how this is being recorded.
Well, that's not really an alligator, it's more like a giant snake. Never mind. There we go. What if that'll appear on the video that Leo was great? Alright. What we want to think about the final velocity is the velocity that's important to Jake when he hits the ground. Not the velocity like after he's hit the ground and stopped, because he doesn't care about that. What matters to Jake is how fast he's going when he hits the ground, because that's what's going to hurt him. Does that make sense to everybody? So make sure you remember that when we talk about the final velocity of an object like being dropped off a cliff or something like that. We're talking about the instant before it hits the ground, because that's what's going to do the damage to someone falling. A lot of my problems involve people falling off cliffs and things like that. And to make up problems, I like to make up. So why is the gain in speed what is the gain in speed per second of a freely falling object? 9.8. Well, this is just speed, so we're going to keep it as positive. Number 2, with what velocity does a dropped object hit the ground if it falls for 1 second? Such a punk, Dean. Oops. 9.8 meters per second squared, or not squared, so we're looking for the velocity. So that'd be negative 9.8 meters per second is how fast it's going. They're saying down is negative, so anytime we have a velocity or displacement down, it's going to be negative. Number 3, an object with thrown is thrown upward with a velocity of 19.6 meters per second. How fast is it moving after 2 seconds? 0 meters per second. Because 19.6 is 9.8 times 2. So it's going to slow down by 9.8 meters per second every second, and after 2 seconds it's going to be 0. Alright, I need to rearrange this a little bit. I don't want the pen. There we go. Alright, so the graph, we have a position versus time graph here, and this is constant velocity. So in a position versus time graph, if you have a straight slanted line, it means it's moving at constant velocity. So what would be happening if this slope of this line changed? It'd be accelerating, right? So what does the slope of this line represent? This line shows no acceleration, but what does the slope of this line represent here? Speed. So if we take the slope of it's going to be rise over run. So it'd be position divided by time, which is 10 meters per second, or position divided by time, or displacement divided by time is going to be velocity. Does that make sense what that graph represents? Okay. So this is accelerated motion now. Now the slope is changing, so we have acceleration. So it means the slope is changing constantly. So at any given point, we can find the velocity of the car by finding the slope of a tangent line at that point, which will make more sense when I'm talking about that when you get a little further in calculus. So to find the instantaneous velocity at the point, you find the slope of the tangent line to the slope at that point. Does that make sense to everybody? All right. This one again is a car moving at constant velocity, except this time we have a velocity versus time graph. What's important about this one is what is represented by the area under the curve. So from there to there, what does that represent? Distance. So we have, to find that area, it's going to be 10, which is the velocity, times 1, which is the time. And that'll give us 10 meters, and that's how far it traveled in the first second. So on a velocity versus time graph, the area under the curve is the distance, whatever object it is traveled. So now we have accelerated motion in a velocity versus time graph. So like we said, the distance it travels is the area under the curve. So what's the area right here going to be? It's going to be 2. So how far did it travel in the first second? 2 meters. And if we did that, what's the area under that curve? What's 12 times 3? 36. It's going to be half of that, so what is 36 divided by 2? 18. So it traveled 18 meters for the first 3 seconds. Does that kind of make sense? And I'll do kind of one more example. What about those two? So what's 16 times 4? 64. What's 64 divided by 2? 32. So that's how far it traveled over here. And what's the area under this part? 8. So it's going to be 32 minus 8. So that is 24. So between 2 and 4 seconds, it traveled 24 meters. That makes sense to everybody? Some questions on graphing motion. Below are both position versus time graphs for objects A and B. Which object has the larger speed? B. I want to use red. No. 2. What does the slope of a position versus time graph represent? Speed or velocity? All right. Number 3. In which of these graphs is there acceleration? And they're technically both accelerating. One's accelerating negatively, one's accelerating positively. So this would be 3 and this would be 3. Number 4. In which graph is there negative acceleration? So which graph are we slowing down? Well, let me rephrase that. We're not actually slowing down in graph B. What are we doing? We're not.
We're speeding up backwards.
We're speeding up backwards. Jake is right. So there's negative acceleration in this one. So what's happening here is the slope is getting bigger, or it's the absolute value of the slope is getting bigger. It's getting more negative. Does that make sense to everybody? That means it's going faster and faster in the opposite direction. So what a slope would look like if something was slowing down, it would kind of look more like that. Because when you get to 0, when it's horizontal, that means it's stationary. Does that make sense to everybody? Number 5, what does it mean if the slope of a position versus time graph is changing? Accelerating. What is happening to the object in the first 5 seconds of that graph? Moving at a constant speed. What's happening to the object in the second 5 seconds? Stopped. Still technically moving at a constant speed, but now it's not moving at all. Now we got plenty of time. Which of the following is true about the graph on the right? The object is moving in the positive direction. Is that true or false? That is true. It's a velocity versus time graph. So as long as the line's above the 0 point on the positive side, it is moving in the positive direction. Is the object speeding up? No. So that's false. It is slowing down. The velocity is getting closer to 0. So is the object slowing down? Yes. Does the object change direction? No. What would have to happen for the object to change direction? Have to cross the line. So if it continued down into here, we'd say it changed direction. Does the object have constant acceleration? Yes. What do you think the slope of a velocity versus time graph represents? Acceleration. So it's a constant slope, so the acceleration is constant. Does that make sense to everybody? What does the slope of a velocity versus time graph represent? Acceleration. And last slide. This is some definitions that will come up on the AP exam. A vector quantity is something that has both magnitude and direction. You guys seen Despicable Me? Yes. The villain's name is Vector because he's committing crimes with both magnitude and direction. That's what that's from. And a scalar quantity is something that has magnitude only, so just a number associated with it, like speed or time. So a vector times a vector gives us a scalar times a scalar gives us a scalar, and a vector times a scalar gives us a vector. Worst part is I make these corrections every year and never bother to actually go back and change them in the PowerPoint. So a vector is kind of like a negative number, and a scalar is kind of like a positive number. that going to make sense to everybody?